Additive manufacturing. As it advances, we see new components, new parts that could only be made through 3D printing. But another possibility is becoming prominent, and it relates to old components, existing parts, the chance to keep them in service longer by restoring them, repairing them, saving significant cost. I saw an amazing example of this in Renteria, Spain, that I want to share with you. Some companies that are all part of the Inzu group of companies, the ones we'll hear from are Izadi and Talon Systems. They're working on this repair system for very large shafts. A wind power OEM came to Izadi looking for this solution. Izadi is a machine shop, machine builder specializing in really big machinery, big components like big gears, big shafts. To get us started here from Izadi is Diego Navamuel.
A wind power OEM requires the repairs process by laser direct energy deposition of the main shafts. Due a new shaft is more than 140,000 euros. The wear is due the shaft service operation time. The bearings where the shaft is assembled wears the shaft.
So these big shafts for wind turbines, they wear in the bearing areas. Sometimes cold spray provides a repair opportunity, but more often the shafts have been scrapped altogether, replaced with new shafts. The cost is around 140,000 euro. Additive manufacturing can save that expense. So Talon's Systems is the laser material deposition specialist. So they're good at directed energy deposition, for example. Their contribution to this shaft repair system is this robotic DED solution, a large KUKA robot carrying a deposition head for applying Inconel 625 material to repair these steel shafts. But it's more complicated than that. From Talon Systems, here is Itziar Anandia.
So each shaft weighs approximately 22 tons and it's 3.3 meters long. The approximate dimensions of the areas to repair by coating with Inconel 625 are: the first one has a length of 650 millimeters and a diameter of 930 millimeters. And the second bearing area has a length of 400 millimeters and a diameter of 820 millimeters. The base material of the shaft is 42 chromium molybdenum 4, and according to the OEM specifications, the material used for the repairing, as I said before, is Inconel 625. The coating process of each bearing area lasts 12 hours non-stop with a powder flow rate of 25 milligrams per minute. It consists of 3 layers of material deposition, having each layer a height of 0.6 to 0.8 millimeters. The 12 hours non-stop is possible thanks to our proprietary and patent-pending automatic refilling hooper, and also the thermal shields designed and developed to protect the robotic optics, our sensors, and the equipment.
So when I was with the team in Spain, I got to talk to them about all the challenges they went through in getting to a repeatable industrial production system for this repair solution. This extension sleeve carries the deposition nozzle. It's also prone to heat transfer to such an extent that it was affecting the optics, the precision and the performance of the laser optics. It took a little while for the team to figure out that this component was the culprit for some problems they were seeing. So redesigning this sleeve to allow for internal cooling to control the temperature, that proved very important to the performance of this system. Here is a broader, bigger, system-wide solution that they developed. It relates to powder delivery. So each of these bearing areas, to make the repair, it requires about 20 kilograms of material, so about 4 of these canisters. There are 2 bearing areas per shaft. The intent is for this deposition system to run 24/7. It's a repair process, but it needs to be a production process too, repairing shaft after shaft. The flow rate of material in deposition is about 25 grams per minute. So how do you maintain that material flow, that controlled rate of material flow, across what could be a pretty long unattended process?
The material is melted during a 12-hour non-stop method, and this is possible thanks to our proprietary automatic refilling hooper that has a capacity for 440 kilograms, and it's designed for a 24/7 production rate. So several R&D activities have been necessary to design and develop this hooper, which guarantees a 24/7 powder supply. We ended up researching and designing a proprietary solution unique in the market and patent pending that enables Talens to provide continuous powder flows of up to 200 grains per minute.
So the innovation is in more than the deposition. Other concerns Talens Systems had to look at: powder characterization. What aspects of the powder are the most important for assuring the flowability they need for this system to work? The custom hopper solution that Talens developed. Software, toolpath programming, for example, getting just the right overlap between adjacent passes to build this repair surface exactly as needed. Melt pool monitoring for ongoing control of the system. Data capture, getting ready for a potential additional user that might have even greater traceability needs, like an aerospace industry application, for example. Something else the team recognized early on: the most effective DED in this application would come from controlling the heat-affected zone right at that juncture where the Inconel 625 meets the steel of the shaft. And to control that heat-affected zone, that meant heating the surface first prior to material deposition. So, how do you heat a shaft that big? Well, here is the shaft preheater that Izadi invented.
This step is necessary to ensure that heat-affected zone is below 400 harness beakers. It has been designed at Izadi facilities and manufactured internally with local suppliers.
The shaft goes in that heater for about 8 hours prior to DED. The pink pieces you see are the heating elements. Ceramic induction heating would have been a possibility. This heater is less expensive than that. So, key points: additive manufacturing as a repair solution. In this case, potentially saving significant cost. But to get to a solution like this, it's more than 3D printing, more than laying on material. This is production too. In a context like this, repair is production. The intent is a system that can run continuously. So to get to that, it meant system engineering, providing for all of the consistency and repeatability needed to run and rely on this process. But the team involved in this solution, they got there. This solution has been realized and deployed.
There are conversations going on, but more or less can be in pre-industrialization phase, 20 to 30 shafts per year. In a full industrialization phase, can be more than 50 shafts per year.
And Izadi is marketing, adapting this system to other potential users who might have similar repair applications. Thank you, Izadi, for letting me visit, see this system, understand it. For even more, Talens Systems, the laser material deposition specialist, I saw another solution they're working on, a very different solution, not related to repair. Talens Systems is also involved in developing a new way of manufacturing automotive brake discs involving 3D printing. I saw that solution as well, and a future video like this will cover that application. So subscribe so you see that one when it drops.